Hello and welcome back to See the Pattern. In part 1 of the Sun series, we looked at the problems with a fusion model of the Sun, and in this episode we will be examining the electric model of the Sun. The electric universe model holds that galaxies and stars are formed via electric currents using the Z-pinch effect, and that these circuits remain open and that galaxies continue to provide electrical energy to the stars. Ralph Jurgens pioneered the concept of an electrical sun, and in this model the Sun receives a fairly steady electrical input from the galactic current that we know exists in our Milky Way and other galaxies. Because of its large size, the Sun has a large capacitance and it exhibits a relatively high voltage. Now, he calculated that the observed power output of the Sun is possible in an electric model given the incoming current that we know of and the Sun's voltage. So how does an electric sun function, and can it explain the phenomena that the standard model cannot? Let's start with the structure of the Sun. If the Sun isn't powered by fusion, why doesn't the ball of plasma collapse due to gravity? The Sun still consists mainly of hydrogen, which is a hydrogen atom, or a proton, and an electron. The hydrogen ions have a much greater mass than the electron, and gravity will act on them with a greater force, pulling them closer together, effectively causing the electrons to be pushed to the surface. The positive ions will repel each other, halting that compression. So again, a happy equilibrium is reached. As the current comes into the Sun, it will cause vast currents to form from the poles right to the equators. Now, the photosphere acts as a sort of barrier, preventing charges from simply racing off the surface, as a certain amount of energy is required to push them up onto the photosphere. At the photosphere, the charges have a maximum potential energy, but a very low kinetic energy. Random collisions may give them enough energy to move up from the surface of the photosphere towards the chromosphere. If that happens, they will experience an acceleration due to the electric field and will gain velocity and acceleration. This will cause the random side-to-side motions that they had experienced before to decrease, effectively dethermalizing them, causing their temperature to drop. At the corona, the electric field potential is lower, and they will bunch up here, and this means that the incoming ions from the photosphere will collide with these ions violently, releasing energy and heat. And this explains why the temperature drops from the surface as the particles begin their acceleration, and why it jumps so suddenly at the corona. A good analogy for this would be a waterfall. At the top, the water must overcome the rocks to begin their descent, and as they fall, they accelerate, finally crashing at the bottom, causing the water to froth wildly. The granulations we see on the surface of the photosphere are not the tops of impossible convection currents. Instead, they are an electrical phenomena known as anode tufts. They are small and bright plasma which form above an anode that is otherwise too small to handle the current flowing into it. In a project called Sapphire, a team of scientists are trying to recreate an electrical sun in their lab, and from their initial experiments they have seen this phenomena recreated as they turned up the potential of the anode. As the potential increases, the number of tufts did too. The tufts appear and disappear as needed to maintain a required relationship between the positive ions and the electron numbers in the total current. These anode tufts effectively allow the discharge to manage itself. By creating the tufts, it creates a larger surface area, allowing the current to dissipate over a larger surface area. The problem is if the current drops too much, then the tuft actually collapses, and when it collapses there is no arc discharge and you can actually see down to the surface of the anode. And in our case, if we look at the Sun, we would actually see into the surface of the Sun and we would see black if this is an electrical sun, and this is exactly what sunspots are. As there is no tufting at these sunspots, the voltage barrier normally presented by the photosphere is gone, so large number of ions can simply flow out towards the lower corona, and these large currents create very strong magnetic fields around the sunspots. And when we view the corona in X-ray, we can see that these higher energetic regions line up with the sunspots. Now, the driving potential of the Sun will actually determine the output power. Now, this can change depending on the incoming galactic current. And in a sense, we can liken the Sun's voltage plot to that of a transistor, where the photosphere is acting like a barrier. If we raise that barrier, it's like increasing the emitter voltage. And by raising that barrier, we can vary the amount of ions that actually flow up onto the photosphere and then out to the corona. And this in turn would affect the strength of our solar wind. And if the voltage was raised enough, then actually we could switch off the solar wind altogether, which has been known to happen in the past. Now, in 2001, the Ulysses mission discovered long plasma tubes that extend from the Sun's south pole all the way out beyond Mars. So if we don't have fusion happening in the Sun, how can we explain the elements that we see when we look at the spectra of the Sun? Now, as the ions stream out towards the corona, their current density increases and filamentation takes place. As we have previously seen, if the current density increases rapidly, the magnetic field can cause a Z-pinch to occur. Now, these Z-pinches could occur in the corona and cause fusion to occur above the surface of the Sun. Now, this would account for the metals that we see in the absorption spectra of our Sun, without the need for a supernova to have created these in the distant past and the dust cloud to have formed the Sun. Hannes Alfvén devised the theory whereby all prominences in solar flares were formed electrically. Birkeland currents follow the direction of the magnetic fields. In the prominence image we are seeing, the glowing plasma concentrates into filaments by the currents that flow in these loops, and these looping currents will create a secondary magnetic field, which is donut-shaped, that will surround and expand the loop. And if the current becomes strong enough, then these magnetic field lines can cause the filament to break. And if that happens, then the stored energy is explosively released into space. We know that as the galactic current passes into the Sun from the poles, we know that secondary currents will flow along the surface of the Sun, and SOHO has already detected these jets or streams of hot electrically charged plasma flowing just beneath the surface of the Sun. Now, these currents create magnetic loops on the surface of the Sun, and if the driving current rises, the magnetic field will point in one direction. But if the current starts to fall, then the magnetic field will reverse. Now, this could explain our 11-year solar cycle, that as we move around the centre of our galaxy, that effectively it has a sheath similar to what we speculate our Sun produces, that causes fluctuations in the incoming current density into the stars. As we orbit around it, we would go through highs and lows, and again, we're not talking about a reversal of the current. We're just talking about the current either rising or the current falling. And as the current would rise, it would induce a magnetic field in one direction, and equally when the current falls, it would induce a magnetic field in the opposite direction, and therefore what you would see is a flipping of the magnetic field in whatever you're driving, and in this case we're talking about our star, the Sun. So therefore, could this explain our 11-year solar cycle, and also the cycles beyond that which are even greater, the 80-year cycle and the 400-year maxima to minima cycle? Now finally, the solar wind. Now we know that the solar wind accelerates, and in the electric sun model we make the assumption that the Sun is a positively charged body, which means that any positive ion that is able to liberate itself from the forces that dominate around the surface will feel an acceleration because of the electric field that it sits in. So this would help explain why the solar winds are accelerated, because they feel a constant force due to the electric field of the Sun, and potentially they are attracted to the electric field that sits outside of our heliopause, so the galactic medium. Now, of course, there are still issues to be worked out in the electric model. There are competing theories that suggest that the Sun is not necessarily positive, but a negatively charged body. Personally, I think the positive model works better than the negative one, but certainly there are competing theories. There are still issues to be worked out in terms of the solar wind, because we know that the particles that constitute the solar wind include electrons. So the question would be, how do the electrons get ejected? We don't have evidence to suggest whether the electrons are actually undergoing an acceleration, because no one has actually managed to monitor the electron progress. We've only really looked at the ions, so we know that the ions accelerate, the positive ions, but we don't know whether the electrons accelerate. But again, I personally believe that this model fits with more of the things that we observe than the fusion model. And certainly looking at the Sapphire project in terms of what they're able to achieve, the results that they're producing are quite striking. Certainly the output from their experiment is yielding very close matches to what we see the Sun producing. But there's still a ways to go in terms of that experiment. So we will watch that and report back on it when more information is available. In part 3, we will be examining the stellar evolution and looking at whether the stellar evolution can be better explained in an electric model. For now, I hope you've enjoyed this information, and as always, be brave, be curious, the truth is waiting for us. Until next time.